Okay, so quiz 1, easy enough? No, wasn't easy. Anyway, let's continue with our lecture. Okay, so we covered KCL and KVL, and then we went into series and parallel connections. Any questions about series parallel connections? Okay, so let's talk a little bit more about series parallel connections, then we'll wrap up chapter one. So in series connections, I pointed out if you have a two-terminal element and you connect one terminal with each other, then we say that those elements are in series. The thing to keep in mind is wherever there is a connection, there should not be more than two connections. Okay, so for example, let's make this bigger. So if you have two elements like this, A and B, we say are in series. However, if you now join a third or a fourth element at the same junction, then they are no longer in series. They're not in series, they're not in parallel. They're just connected together. And that's it. So again, the most important thing to keep in mind is that it's a series connection as long as there are no more than two connections at a junction or a node. Electrical junction is also known as a node. NODE. Okay. Then we talked about parallel connections. And in parallel connections, I said two terminal elements, A and B, have their respective connections tied together, or basically connected together. So if those are connected together, then we say that the elements are in parallel. Okay, they are in parallel. In the example on the left, we had A and B. A and B have both of your terminals connected together. The black dots that you see simply indicate that there is a connection between the three terminals. That's all. So that's a node. And this node, again, taking a little segue, if you remember, I said you can draw the circuit schematic in many different ways, right? So this one is just drawn at an angle. That's how, schematics are drawn typically. So nice and clean. However, I could also draw it like this. This would be C, this would be A, and this would be B. It's still the same connection. It doesn't change. Okay, it doesn't change. Again, this is just for your understanding. You will not see a circuit that looks like this. Most of the schematics will be like this. Nice, clean, and rectangular. On the right side, we have D, E, and F. D, E, and F also have the same connections. Both of the two terminals are connected together or connected to each other. And so we say D, E, and F are all in parallel with each other. Okay, they're all in parallel with each other. Now, whether it's series or whether it's parallel, you can have infinite components all connected to each other. Remember, like the holiday lights, Christmas lights, right? Nowadays, they are wired a little bit differently. But when they first came out, what they did was they would have a bunch of light bulbs connected in series. Okay, a bunch of light bulbs connected in series, and each bulb could handle about 2 or 3 volts. So if you, let's say, for instance, if it could handle like 2 volts, then you connect 50 light bulbs in series, or let's say 110, right? 55 light bulbs are connected in series. and you plug it into your power outlet, now the electric current is passing through all 50 of them. And it's split equally across every single light bulb. So again, whether it's 50 or 500 or 5 million, you can have a series connection as long as no more than 2 terminals are present between each junction. So a series light would look something like this. And so on and so forth. And you would take plug light bulbs. So the current actually comes from your power outlet, goes through each and every light bulb, and goes back in there to form a closed electrical circuit loop. Again, remember, current needs a closed pathway to flow through. If it's open, it doesn't work. So in the older circuits, if one of the light bulbs blew out, your entire light series would stop working. And that was the reason why that happened. So it's a series connection. If one of the light bulbs blew out, then current no longer has a pathway to flow through, and your lights stop working. Okay. Even in modern lights, there are divided into multiple sections. So there's about 3 or 4 sections in each light. Depends on how they designed it. And so if one light bulb in one section goes out, all the light bulbs in those sections will stop working. Anyone ever experienced that? Right? So that's the reason why. Because they divide it into multiple sections, all of those sections, let's say there are 4 sections in a series of, I don't know, like 50 light bulbs. So then they would, all the 4 sections would be connected in parallel, 1, 2, 3, 4, but then all the light bulbs in each section would be in series. Okay, they would be in series. So if you plug in, let's say, you buy 2 of these together, right? You have one series of lights, you buy another series of lights. So at the end of the string, you would have seen there is a power outlet socket. So you can plug in another series light directly in there. Again, anyone ever notice that, right? And what you're doing there is you're simply taking the second one and you're plugging it in parallel to the first one. That's all you're doing. So at the end of that string would be a connection that comes from here. There's a, and this would become a socket, and you would take another light string and plug it in here. And thus they would be connected in parallel. So you can have longer and longer and longer series of lights. So again, series and parallel connections, this is an excellent example. I always like to use it. It's something that most people have either seen or they have actually worked with. Light bulbs all connected together in series. If one of the light bulbs stopped working, the connection is broken and current can no longer pass through. Now it's a parallel connection. Obviously, one section can go out, but the other sections will keep working. Okay. Similar to series, parallel connections can also have infinite number of components, so you can keep plugging in. Well, in real life, of course, there is a limit to how much current and voltage can come out from a power outlet. But theoretically, you can take one power outlet and you can keep plugging in as many light series as you want. As long as the power rating for that electric loop does not exceed as long as the power rating is not exceeded, you can keep connecting as many as you want in parallel. As the same concept applies, you can have infinite connections in parallel as long as both terminals of each component are connected to the other ones respectively. A and B, 2 elements in parallel. D, E, and F, 3 elements in parallel. You could put in like G, H, I, J, K, as long as, as many as you want. Infinite connections possible. Now, at this point, we don't know what these elements are, right? This is just to point out series and parallel connections. The three components we study in this class are resistors, capacitors, and inductors. All three of them have two terminals each. And you combine multiple resistors together and you can reduce them down to one. That will simplify your circuit analysis in many cases, okay? If A and B were like resistors, you could combine them together and make it as one single resistor, mathematically speaking, okay? Physically, of course, they remain two, but electrically speaking, the circuit would see it as one. And so mathematically, what we can do is we can reduce these resistors down to one single resistance. Same thing with a capacitor and same thing with an inductor. Doesn't matter how you connect them, whether you connect them in series, whether you connect them in parallel, it is possible to reduce them down to one single element. And so that is what we did in this example here. We reduced A and B down to one single element. We reduced D, E, and F to one single element. You do not forget, let's say this is 1, this is 2, this is 3, this is 4. Do not forget the terminals where you have connected them to the main circuit. Okay. Let's take a 10-second pause, think over this, and let me know if you have any questions. Again, this is critical. I know most of you might be familiar with this, but again, this is very important because when you get to larger circuits, you need to be able to visualize and analyze circuits very, very quickly. So again, series and parallel connections, very important. Any questions? Okay. Then I believe this should be the end. We covered KVL. Was there any questions about KVL? Practice KCL and KVL problems? Anyone? Okay. So that is the end of chapter 1. Let's begin chapter 2, which is resistive circuit analysis. And let's see. We need to share and okay, resistive circuit analysis. This is, well, by far, I would say, is the most important chapter for this entire class. Okay. What happened to the pen? So we talked about series and parallel connections. Let's look at resistors in series, and then we'll look at resistors in parallel. Again, I realize from physics, you would be familiar with this, but again, very, very important. Here we have 3 resistors in series, R1, R2, and R3. The way we determine, well, that they're in series is R1 has 2 terminals, R2 has 2, and R3 has 2. Connected together, connected together. And so we can say R1 and R2 are in series, R2 and R3 are in series, and then the outer terminals are right here. If you connect a meter, multimeter or an ohm meter to measure the resistance at those outer terminals, they will give you a reading. And that reading, we call it as the equivalent resistance, or REQ. Okay, REQ. It's the equivalent resistance of the 3 resistances in series. And of course, there is a derivation. Derivation simply is determined from the current I that would be flowing through that circuit. So it doesn't matter what current what current flows to the circuit, the value does not matter. The derivation simply states if I is flowing through a circuit, the same current I is going to flow through all three resistances, right? There is no other pathway for the current to flow through. So it flows through all three of the same resistances. So the voltage drop across each one would be given by Ohm's law, V equals IR. So the voltage across R1 would be R1 times I, right? Easy enough. Voltage across R2 would be R2 times I, and across R3 would be R3 times I. I is common, you take it out, and you apply Ohm's law in reverse, and you get Req as simply the sum of the three resistors in series. Okay, the derivation, as I was saying, if you apply voltage V, it could be split across the three resistances. Here I could say it's I times Req. This would be I times R1 plus I times R2. Oops. Plus I times R3. I cancels out. All you're left with is R1 plus R2 plus R3. Derivation is just to show you, how the concept works. So you don't have to memorize the derivation. What you need to understand is that resistors connected in series, if you want to find the total equivalent resistance, you simply add them up. And at the outer terminals of those series connections is where you will find the total Req. Yes, did you have a question? Okay. Easy enough, right? Resistors in series, doesn't matter how many you have, 5, 10, 15, 20, 100, thousands, millions. As long as they're all in series, simply add them up and you get Req. Resistors in parallel, very similar derivation. You're applying a voltage across a parallel connection that will cause a current to appear across current to flow through each resistor. And the total current in that circuit would be the sum of the three currents IR1 plus IR2 plus IR3. You apply Ohm's law, I would be equal to V divided by Req, right? V equals IR, so I equals V over R. So total current in the circuit I would be equal to V over Req. And then you would derive the equation for Req. And that simply turns out to be this. The total equivalent resistance for resistors connected in parallel is the reciprocal of the sum of the reciprocals of the resistances. Quite a mouthful. But simply what you do is you take reciprocals of all the resistors in that parallel connection. Doesn't matter how many they are. Go on to infinity. One over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3 all the way to infinity. As long as they're connected in parallel, the same equation applies. And the reason it's 1 over Req is because Ohm's law, the current I gives you voltage over resistance V over Req. Okay. It's all familiar from physics, I hope. How much time do they spend, by the way? I ask these questions of the physics professors, and like, the number kind of varies. They spend like 2, 3 classes, more than that. Okay, 2 classes. Okay. All right, any questions? Again, the reason I go slowly at the beginning again is as I explain, everything on this in this class, especially the first 2 chapters, is built step by step. So we learned about KCL, KVL, series parallel connections. We learned about resistors in series and in parallel. We'll go to voltage division, current division. That builds off of this technique right here. Okay. Equivalent resistance for these circuits. Never seen resistors connected like this before. Maybe, perhaps. No. So nothing to be worried about. What can we say about these 3? They're all in parallel. Once you find the equivalent resistance for R2, so A, R2 in parallel with R3, which is in parallel with R4. You can name this anything you want. I simply take the subscripts and combine them. So I might say if this is R1, R2, R3, R4, I'm going to call this R5. But you can name it anything you want. You can call it R Batman, Superman, Iron Man, whatever. Doesn't really matter. Or you can sometimes just combine the 2, 3, 4. So it says R2, 3, 4. Right? Doesn't matter what it is. Then, if we combine it together, what can we say about the relationship between R1 and R5? They're in series, right? Now, again, it might be quite obvious to some of you, but I need to ensure that it becomes obvious to all of you. Like you look at a circuit and you should be able to identify within a few seconds which components are connected in series and which are in parallel. Again, but proceed step by step. So this is R1. This is now R5. You can now find Req between the outer terminals. And Req is simply R1 plus R5. My strong advice would always be do not rush things. Always take it step by step. Okay, when you rush things, that's when I see students make mistakes. One of the most common ones I've seen students do is if they have a circuit like this, they would take R1 and R2 in series, and then they would say that the combination of R1 and R2 in series is in parallel with R3 and R4, which is quite understandable. So again, you start at the opposite end from where you're measuring. Okay, if you're measuring Req at these terminals, you start at the farthest end and you reduce the circuit towards your measurement terminals. Okay, reduce in that direction. Do not start from the terminals itself. If you look at the circuit from the terminal itself, yeah, you might think that R1 and R2 would be in series. But at this junction point, you have 3 connections. So there's no way it could be in series. So always start at the farthest end and then move towards the terminals, reducing it step by step. Okay, let's take C first, then we'll take B and D. What do we see in C? Yep. So the answers were parallel, parallel, and then in series. So we start at the farthest end. We see R4 and R3. So the farthest end, R4 is in parallel with R3. Let's call that R5. And then we cannot reduce it any further. We cannot reduce it further until we reduce R1 and R2, right? So R1 and R2 we can see are in parallel because their connections, I mean, their terminals are connected to each other. And so I can say R1 is in parallel to R2. I'll call it R6. And then finally, R5 and R6 are in series. Make sense? We are at the end. Let's see. Series parallel equivalence. Think about B and D. Just think of it in terms of the concepts we talked about, right? Two terminals connected to each other for parallel. Series connection, only one terminal connected together. And if you take it step by step, you should arrive at the right answer. So we'll end class here today. We'll meet again tomorrow. If you have any questions, I'll be in my office during office hours.
Thank you.